Okay, Paul here, and I'm continuing to work on this Halton radio. And we noticed in the first video that it played pretty good, has good sensitivity and selectivity. That's pretty common for these simpler radios, these All-American 5. Actually, it's a very good radio. It's a quality made radio, and at this point in the 40s, late 30s, early 40s, they pretty much figured out how to make a super heterodyne radio in very good shape as the All-American 5 with a lot of capability. But in this video, we're going to go ahead and start doing a capacitor recap, but I also want to show you why we recap capacitors. I'm going to start with this replaced electrolytic, and we're going to check it on the meter and see what it is. You see, I turned it so you could read it. I guess you could read that. It says 50 microfarad at 150 volts, and another 50 microfarad at 150 volts. That capacitor was replaced. You open up the schematic here, and I'll tell you what that should be. Okay, those should be rated each 30 microfarad at, let's see, 30 microfarad doesn't say what voltage, but I would imagine they were, 160 volts, 150 volts, that's about right. So what we're going to put in there is what's supposed to be in there. Now the 50 is fine, going up is fine, but you don't want to go up too much, because then you're going out of the spec of what the engineers had designed. So rather than go up, what we're going to put in is these 33 microfarad capacitors, which is, and these are Nichicon, they're good capacitors. These are what's supposed to be in there, 30 at 150 roughly. This is a 33 at 250, so it'll handle whatever voltage you plug this into as far as the capacitor anyway. It'll handle up to 250 volts, so you don't have to worry about 110, 117, 120 volts. It doesn't matter. The capacitors will be overrated. This capacitor is overrated. They rate all capacitors overrated. This is one of the highest ones I've seen in a wax capacitor. It's saying 600 volts at rating. Most of those capacitors are nowhere near 600 volts. They're usually 250, like this one that was replaced. Let's see what he is. He's 600 volts too. They're usually 250 to 450, sometimes 350 volts. But the ones we're putting in are rated at 630 volts, so they're even better than these. So we don't need to worry about that. But we're going to start by checking the capacitance on this capacitor, and I'm going to leave it in circuit. The tubes are removed, so it doesn't matter. As long as I take the ground off, I can measure across the ground and the hots, and it's out of circuit, so it's the same as taking the whole thing out, which we will do. But let me go ahead and see if I can unsolder that. If not, we'll just cut it out. But for right now, I'd like to try to just actually, you know what? I'm just going to cut it out. Because I know we're replacing it, so there's no sense in leaving it there. Now, when you cut capacitors out, the people who are working on these, leave some lead. There's no reason to take all of the lead out. Two reasons. One, it lets you know exactly where it goes. And two, when you put new capacitors in, especially on these old wax capacitors, if you leave a lead, I can show you the easiest way to install capacitors without having to worry about a bad solder joint or or the wire being loose on one side, but we'll look at that. Okay, so let me strip this. All right, now I got these wires connected to the probes on my meter, so we can go right across it. So I'm going to put this on the negative lead, and we're going to check the capacitance on both of these two capacitors that are in here, both 50s. We'll check this one first. It's this red wire goes to this terminal on this tube socket, so we just connect on there. And that should be 50. And look at it, 120 microfarads, 125 microfarads. Actually jumping around, but okay, so 140 microfarads. That is way out of spec. It's 50 microfarads. This guy here is 50 microfarads plus or minus 20%. So that would be 40 to 60. My math is right. Let me double check, make sure. 50 plus 20% equals, let me try that again, I hit the wrong button. 50 plus 20, yep, 60. So plus 20% would be 60, minus 20% would be 40, and this guy, look at, he's still changing as it's just sitting there. You see how it's just switching around? That capacitor is toast. It's over 100% out of tolerance. And this is why we have to change them. It would be just a matter of time that that capacitor would burn out that tube. So now we'll check the other capacitor in here, which is this red wire, and it goes up. It's a little hard to see here. It goes up behind this resistor and behind that capacitor there, and I'll know it because when I hit it, and I believe it's here, I'll get a reading. There we go. And look at that one. Again, all over the place, because this is a dry electrolytic and it is really dry. But look at that, 146 microfarad, 137 microfarad. It's jumping around, so it's around 140, about the same as the other one. And we may be getting some stray there. No, yeah, a little bit. A little bit of capacitance between the leads. Let me just move that one over there and we won't have that problem. Okay, so 130, look at that, just jumping all over the place. That capacitor is dead. Now let me show you what happens with the new capacitor that I'm going to put in. Here's one of them, and this is the ground side, and this is the hot side, and it's rated at 33, so it's 33 plus or minus 10%, 20%. Okay, so 33, 10% would be 3, right? 3.3, it's 1/10 of 33. 20% would be 6.6. So anywhere from 39 to 27 would be intolerance. Look at this thing. It's it is 35 instead of 33. You talk about accurate. That thing is accurate. And you notice it's not jumping all over the place. It's 35.0 and it's staying there, even though my meter is charging it up. Okay, so let's try the other one. Here's the other one, same batch. And again, very good capacitors. And look at 35.01, oh, 35. So again, it can be anywhere plus or minus 6 from 33, so 27 to 39, and we're 35. We're right in the middle of the range on the top side from 33 to 39. We're 35. What a difference versus a 50 being 140. So you see why it's critical to change capacitors. So we're going to change those two. Again, what I'm going to do is just cut this one out. I'm not even going to bother unsoldering it yet. And again, I'm going to leave a little bit of the lead just so we know where it was and we don't have to guess. And on this side, since I got all this under here, I'm going to cut it way back here. And that way I got plenty of lead in there to find it. And we'll go ahead and slide it out of its connector here. Okay, and just so you can see that it's definitely bad and that it was checked even though it was still connected on one side, I'm going to go ahead and show you again that this thing is toast. Okay, so we connect the negative here, positive on one of these, and look, it's supposed to be 50. Look at that, it's 80. So out of the circuit, there's no stray capacitance, but it's 78 instead of 50. So it's 50% out. It's definitely bad. It's over 50% out. It's almost 60% out. So it's totally bad. This side, 82. Again, 50 to 60% out. So you can test them in circuit. They're going to be a little bit higher because of inductance around where you connected them. But you see, that's what it is. And then see if I go back to the first one. '79, '78, '79, '78. It's jumping around 77. So it's definitely got some internal leakage, or it wouldn't be jumping around like that. But you see where it's staying at, 78 now, 78.1, 78. Okay, so that's way out. Again, it's over 50% out. 50% of 50 would be 25, so plus 25 would be 75, and look at where we are. We're above 50% out on a plus or minus 20% capacitor. That capacitor is bad. Now it's ironic that it actually has some capacitance left, but you see how that turns even with this standing here? That's what I'm talking about, a dry look. Hear it? It's dry in there. It's dried up. And it's a nice one. It was made in New Jersey. You know, that's interesting. It's got a U.S. Patent Office stamp on it. Made by Cornell Electric. And whoever installed it put a price on it. I can't quite read it now. It got smudged when I took it out of the clamp, but it was $2 and something, $2.80 it looks like. No, I'm sorry, that's not $2.80. It's cheaper than that. Anyway, but a capacitor like this now, if you was to buy one in this kind of shape and this kind of case with this kind of thing, would be, well, one, you couldn't get it, and two, if you did, it'd be made in China and it wouldn't last at all. So we got these new electrolytics. The other thing is the technology. Look at that. These two is inside one of them. Look how much they shrunk over the years. That's just amazing. And this is over 100 volts more than, it's 100 volts more than that. So these are bigger than this one. But we're going to put those in. Okay, so we know where they go. They go from ground, which is actually on this unit, chassis ground. You see that wire goes right to the chassis. So we're on chassis ground, and goes to that tube and that tube socket. And that's the B plus line here, going to these three tubes, and on that it's the rectifier, or the output amp, I'm not sure which, it's one or the other. I think it's the rectifier there, the 35Z5, I believe, was in the front. Yeah, because this goes to the amp. That's the 50L6. So this is the rectifier here. So one of the leads goes to the rectifier directly, then it goes through this big power resistor, and then it's smoothed again with the other capacitor, which gives a smooth DC on the bus line, on the B plus. Okay, but to get that in there, to get those in, we got to get this mess out of the way anyway. Let's go ahead and look at these sockets. Breakers. My meter wants to shut off to save power, so we'll turn it down for a second. Save battery life. Let's go ahead and take this guy. Actually, this one would be easier to get to. Let's go ahead and start with this one. Let me turn this so you can see it. Okay, so I'm going to take this one out. And I'm going to, like I said, I'm going to leave the wire in there, pull it all the way this way. And I find my clipper that I put down somewhere. Disappeared. Oh, I dropped it, that's right. Fell on the floor. Just a second. Okay. I'll just move that over that way for a little bit, and I'm going to cut it right up here. I'm going to cut this side right over here. Again, I'm leaving some strand of wire there, so I've got a connection there and a connection here, which we can take that off now. There we go. One there, that's where this guy goes. And he is a 0.05. So that would be this guy here. And so if we check him out, he's supposed to be a 0.05 at 600 volts. Let's get back on, meter back on, and turn it back so you can see the meter. Okay, we're back on nanofarad scale, which is capacitance scale. And I'll put the black lead on. And on this capacitor, this is considered the foil side, has that line. It goes to the most negative side of the circuit. Doesn't matter on new capacitors, it mattered back then because these were foil wrapped capacitors. And this lead here, it's a foil that's wrapped in a spiral out from the center out to the outer case. And this side represents the outer case. In fact, it probably says outside foil. No, it doesn't. Some of them actually say right on the black line, outside foil. But anyway, it's a 0.05, 0.005. I'm on the nanofarad scale, which is 1,000th of a microfarad. So this should be 0.005, which would be 5,000ths. Of a microfarad scale. So is this. So we should have 5, and we have almost 8. So this thing is way out of tolerance. It's supposed to be 5. It should be plus or minus 20%. 10% would be anywhere from 4.5 to 5.5. We're getting 7.9. So let's check the one that's going in there to replace this dude. Again, doesn't matter how you connect these newer ones, they're Parley and they're COVID. But look at that. It can be anywhere from 4.5 to 9 to 5.5. This one is rated at 4.7, which they don't make 5 anymore. They don't make 0.005. This is a 004.7. Of course, I got it upside down, but you can see it there, 472. So it's a 004.7, and look at what it rates, 4.752. Now, I don't know if I can switch this to microfarads. Okay, there it is on the microfarad scale. And so on the microfarad scale, it comes out to what this is supposed to be, right? 0.005. it's actually 0.004, but because I'm on a high scale, it's just rounding it off to 0.005. Perfect, perfect. And on this scale, if I measure this one on this scale, well, this should be the same exact thing, 0.005. You'll see it's 0.007 or 0.008, 0.008, way out of tolerance. It's absolutely no good. There's two problems with these wax resistors. We just looked at one of the problems, and I'm going to turn this down. We just looked at one of the problems, and that is that they're out of tolerance. They're out of the plus or minus 20% tolerance. Doesn't even say on this one the tolerance, but it is. They're all 20% wax, and they melt and they get hard and everything else. It's all sticky and gooey. It's wax-coated paper on the outside. Whereas this is nice polypropylene, poly capacitor, so it's got a nice hard case. Polypropylene. Anyway, this is one problem. It's out of tolerance. The other problem is DC. These capacitors are not supposed to allow DC to go through. So let's see. Usually you use really high voltage to check a capacitor for DC leakage. But let's see if anything gets through this capacitor. Okay, look at, oh, did you notice that? Well, first off, it charged. I'm on a megohm scale. So now there's nothing leaking at this low voltage of my meter. Okay, notice the difference. That one didn't even move. And if I turn it around, now it's charged, it should move. It didn't even move. Didn't even move. No DC at all going through this capacitor. Take this one again. Watch the meter. See that? That was leakage. That was DC going through the capacitor before the capacitor built up a charge. Once the capacitor built up a charge, DC is, it's now plus to plus, so it can't travel, right? Because electricity goes from negative to plus, negative to positive. So right now we charge the capacitor. That's what the numbers were. They were climbing up. Let me turn it around. You'll see what I mean. Notice you have to look fast because the numbers flip fast, but you'll notice they're going up until finally they're OL, which means out of range, over. Okay, here we go. See how it's going up and then it stopped? Now we got more negative here opposing this negative and positive here opposing this positive, just like a magnet, right? North with north, they repel. South with south pole, they repel. Same thing in electronics with electrons. So, but that's supposed to be always the case. There should be no DC going through the capacitor. So that capacitor is really bad. See? Nothing. Nothing at all. As far as my meter's concerned, measuring the resistance on this capacitor, it's like a fuse that's burnt. It's like there's nothing there. There's no connection at all. Now with AC there is, which is supposed to be. Capacitors are supposed to allow AC to go through, but not DC. This capacitor allows DC to go through. Now we checked it on, I think I got 1, 2, 3, 4, maybe 6 volts DC here. And at 6 volts DC, power is getting through this. That's not good, because this radio runs at 140, 150 volts DC on this hotline. 150 volts going through this instantaneously to the grid of the tube here is enough to burn out this tube over time. Turn it on, turn it off, turn it on, turn it off. You got 150 volts shooting into that tube, where it's only supposed to be millivolts. And that would be AC only, no DC at all. But this is allowing DC right to that pin of that tube. So we're going to replace that. Now I'm going to show you how I replace this. This is a trick. There are a lot of different tricks to solder these. Some people will take the wires here. Let me turn my camera so you can see. I'm going to shut my meter off. We don't need the meter for this step. Some people would take this wire and this wire here where we cut it out, and they would make a little hook like this in this wire and a little hook on the other side, and then they would crimp them and solder them. And you can do that. You can hook and solder. As long as you have some kind of thing like a hook and a hook, and then you solder it. It's all right. That's acceptable. Other people will take this, and what they'll do is they'll take this lead and the piece of wire that's there, and they'll just overlap them like that, and they'll put solder on them. That is not acceptable. That's going to let go. That's called tacking the connection. And we do that. I do that. If I'm testing something, like say I wanted to play this radio before I cut this one out with the new electrolytics to see how much of a difference it made. So, say this radio had a hum. Well, that would be this guy that would make a loud hum if it was worse than it is. I would put these in and play the radio. I might just use jumper cables and jump it in, or I might just tack it in, which would be just to solder the wires like that. Because I'm not going to leave it there. It's just to do a test. That's okay. But if you're planning on leaving it there, that is not okay. So hook to hook is okay. But a better way, and I will show you this better way, is get something that has a nice, not so clumsy. Okay. Get something that has a nice solid wire. See, this is an electrolytic, an old useless one. 10 microfarad at 25 volts. It's just dead. But I keep it handy because of this. See how tight that is? Nice and solid. That's good. And what you do is you take your capacitor. Now you got to decide, do I need to put shrink wrap on this capacitor? Well, since this capacitor is going across a very small gap and there are no other wires that can touch it, and it's not in a circuit that requires RF protection or anything like that, not that shrink wrap would help with that, there's no reason to put shrink wrap here. You don't need it. So since that's the case, and I don't have a lot of room in here to solder, I'm not going to worry about shrink wrap because it could just melt with the soldering iron and stink, and it's just not needed. But what you do is you take this and you put it about where you want the lead to extend. So I want it pretty close, actually. I want it about there. I don't have far to go, like I said. So right about there. And you kind of got to hold them both. And you wrap this lead around, and just wrap it around about 3 or 4 times like that. Okay? Now that's a sloppy wrap. If I didn't have to have this so close, I could have made that a lot neater. But since it's a sloppy wrap, what I can do is fix it with some pliers and just crimp it together like that. Okay? And it should be kind of snug, so you can pull it and turn it if you need to tighten it up a little bit. You see how that tightened it some. And get it together so it's nice and neat. And then you can just slide this out. Now, normally I would leave that on and cut it later, but since it's a tight area for my soldering gun there, I'm just going to go ahead and cut it off. I know that this is fine. I don't need that piece of wire. Throw it away. Don't leave any loose wire on your bench, because if you do that, you're looking for an opportunity for a short when you're flipping things around or whatever. And you sure don't want to cut it in here and leave it in here, because See, like somebody dripped solder there in the manufacturer and they left it there. Well, that's solder and it's stuck to the chassis, so it ain't as bad as a loose wire that can float around and hit something. But you take that coil and you see how easily that slides over the existing wire. And if you want a tight area like this to solder, you can hook this on something up here. Doesn't matter. Just to keep it there. Put a drop of flux on it. Don't need much, just a drop. Well, the flux is not coming out though. You need some. Apparently it got blocked since last time I used it. Okay, sorry about that. I had a little issue with this squirt bottle. All right, so we want to put a drop on there, just a drop. Like that, that's all you need. And then that'll get the flux to flow. Take your gun, take your solder, put a little spot of solder on the soldering gun, let it heat up first, and then just touch it like that. And that gives you some, I have to do this one left-handed because of where it is, that gives you a connection to the outside of the thing. And then you put it on one side of the coil, and just touch the other side. Oh, hold on, let me get this. So I'm not going to touch the soldering iron and cut my solder off. Okay, let's try that again. Get it hot, let the soldering get hot, and then touch the solder and just touch that. And it don't take much, just a little bit. Let it cool off. You can blow on it a little if you want. And see, that's a good, see how tight that is? That's a good electronic connection. And that's what you want. Then the piece that's sticking out, that little spike that's sticking out, get in the habit of cutting them off, but hold them so you don't, see, there it is, on the tip of my finger, so they don't fall inside. But get in the habit of cutting them off, because in a high IF area, they can actually interfere and cause noise in the system, so you don't want them. Now this is not a problem here in this area. It wouldn't have mattered whether I cut it off or not. But I do that anyway because it's just a good thing to do. Now I can bend this a little bit, and that's where I'm going to put the next one. So again, I can take my wire here, get close to the capacitor, and just wrap it around. And then I'm going to just cut this off because I know I've got plenty. Throw that away. And then get it together. Doesn't have to be perfect, just close. Just enough so that, you know, it looks nice. It's more cosmetic than anything else at this point. Push the wire through somewhere where you feel comfortable that it looks all right. Put a drop of solder, flux on it. And you can use paste. If you rather use paste, you don't have to use solder flux. Liquid flux, you can use the paste flux. But you just want to put a little bit on it, especially since the old wires, one might have wax on them. Of course, the gun will melt the wax right away. But they might have oxidation. The solder may not want to stick. You don't want, let me get hotter. You don't want a cold solder joint. You want a nice, shiny solder joint. See that? And you know, when you let it cool, you know that you got a good connection because it's not sliding up and down a wire. You can see, pull it in here. You can probably see that. You want it to be shiny like that. And you want to make sure that it doesn't slide up and down. But that's a nice tight fit. I'm pulling hard and that ain't moving. So that tells you right there that you got a good solder joint. Now without the flux, that wouldn't have happened. So you got to use the flux. Again, cut off the excess so you have a nice piece there. And then if you want to make it look nice, you can kind of bend the leads however you want, just so that it looks good and it's not near anything else. You know, this is a ground wire here, so you definitely don't want to be connected to that ground wire. One side of this resistor is go into the capacitor we just put in, so we can actually fix it, make it look better. They just kind of pushed it in there. But that's good. That ain't no problem there. That's a nice connection. And there's one thing I usually do that I didn't do on this one, and maybe I can fix that. I kind of failed there. Get in the habit of facing the codes out, so people who work on it later can see the number and know exactly what's there without having to cut it out. Now here it didn't really matter because I had plenty of lead to turn it back, but sometimes you can't turn them. And the bigger ones, with the bigger capacitors, you don't want to go turning them too much because you could break the lead off. But these little ones, and in this, with a lot of lead like that, you got room to work if you make a mistake. But get in the habit of doing that, and that'll help. So what I'm going to do is now continue that same process on all of the capacitors. This one here is a real pain in the neck. I got to get it out of there, and you're going to run into this a lot where when they assemble, they stop from the bottom and they work out. In this area where you have the amp, the diode, and the rectifier, the amplifier, and another tube like this really close. On this side of the radio, you're always going to have a lot of stuff. Sometimes they have it all congested on the antenna side, like this tube may be here, this tube may be over here, and you have everything congested there. When it's congested like this, it's a little more difficult. So what I normally do, and again, this is just the way I do it, you can do it however you want, is I'll do the same approach, but when I cut the wire, I'll cut it a little bit closer to the capacitor, so I have a longer wire sticking out here, and I'm going to trim that later anyway, but I move it to the side. This one here, same thing. I'm going to cut it closer to the capacitor, leave just enough room. Sometimes you can't leave any, you can hardly get the cutter in there. But cut it and leave plenty of room to get that out of the way, but where you know where it is. And now I know that there's one that goes across there. It's this 0.01. So now we're going to check this 0.01 and see what it's showing. So let me get my meter back on, turn you back where you can see it. This cabinet just a little bit, okay. All right, so now you can see the meter. And we're going to go back onto the, on the wrong one. Go back to the nanofarad scale, and we'll check this guy. Now he's a 0.01. And watch the meter, and we have 0.015. That's not too bad, actually almost 0.016. So this is a 0.01, it would be fine from 0.012 to 0.008. And you can think of the 0.0 here because of the scale we're on. So we're on 0.015, almost 0.016, which means it's over 50% out on a 20% microfarad capacitor. So this capacitor is bad. Again, if we go to the ohm scale, let the meter settle up, I touch it, notice DC leakage. Look at that. Really slow charging too. It's charging, but there was DC leakage when I first connected it. Now it's charged. Now this one will do the same thing, the replacement for the 0.01. That would be this guy here. It's going to charge, probably charge too, but watch. Oh, nope, instantaneously charged. Wham, full charge, just from the time I connected it. Turn it around. You see how fast that went? As soon as I touched it, it has a charge on it now. When I turn it around, now it's like putting the south pole of a magnet with the north pole of the magnet. They attract, so there's going to be current, but watch how fast. See that? Again, the old wax one, that's way out of, it's also out of value. but the charge, look at, not good. Turn it around. Look at it. Look at that. Look at the bar on the top of the meter going across. That's how long it's taken to charge this capacitor. So where's the electricity going? If it's taking that long to charge a capacitor, I'll tell you, the electricity, the DC current, is going right through this capacitor. This capacitor is designed to stop DC. It's supposed to be a roadblock, so DC can't go through. But you see how long it took to charge. That's how much DC is going through this thing. Again, very bad for the tubes and bad for the IF cans, which could really burn up. See, that connects to the tube with the IF can right there. So, you know, really bad. These things are way bad. They got to be changed. That's why I tell people when they buy a tube radio or any kind of tube amplifier that's got some age, don't just plug it in. You need to put it on a current limiting light bulb or some kind of current limiting circuit, and you need to bring the voltage up slowly with a variac. If you plug it in, you could burn out something that's seriously irreplaceable on the unit because of bad capacitors. These are bad, but even bad, this radio worked, and worked well. So just because a radio works doesn't mean you should plug it in and use it without having it serviced, because this could destroy the radio. So the other thing is the code numbers on these tubes, on these newer capacitors, are all over the place. So make sure, even though you think you know what it is, it's so easy to make a mistake because of the letter sequence that has to do with the tolerance and all of that. Go to the nanoscale, nanofarad scale, and check the capacitor. Make sure you know what you got. It's supposed to be 0.010, and we got 0.01012. Again, because of the scale I'm on. If I go to the actual microfarad scale, 0.01. That's exactly what it's supposed to be, 0.01. Okay? Now I'm used to using the nanofarad scale and moving the decimal point myself because it's much more accurate. It goes 4 digits. So it's 0.01012. I mean, that's really an accurate scale. I like that kind of accuracy, so I use the nanofarad scale. But I take this one and I take this one. I know they go together, and I know it goes here, but I'm not going to put it on yet. It goes from here to here. If you don't feel comfortable not putting one on that you just cut out, then take a piece of paper and write on it, 0.01, 0.01, and put, maybe, or letter A, and then the next one B and B, and tape them on there so you don't get confused. But I've done enough of these to know what I'm doing. And I only wanted to get that one out so that I can get this bottom one out, which goes to ground. Now, what I'm going to do is, it's in a black coat insulator up there, so I'm going to cut it close to the insulator. If I can get in there, okay. And then I'm going to cut it here where it connects to ground, but again, close to the capacitor. And now I can slide that capacitor out. To move that wire out of the way temporarily and slide him out. Okay, so this is the one I'm going to put in now instead of the one that I got there. But I got those ready to go. I already know what it is. This is a 0.05 microfarad capacitor, okay? And it is sticky and gooey. It's a Sprague, which means it's not, I don't think that was a Sprague, no. This is a Sprague capacitor, so they put a good one in, but this one you can see, it is sloppy. What I suggest for This stuff, if you're not wearing gloves, which I usually wear gloves, but because of this video I didn't want to wear them, keep a piece of paper towel handy with some isopropyl alcohol on it, and you can wipe your hands. It'll take that right off. It'll also take the flux off anything like where the flux before. You can wipe it right off with this alcohol. The problem is finding this stuff because of the coronavirus and everybody hoarding it. So we put this on here, this gooey thingy, and you see it should be 5, and it's 7,537. So it's really bad. It's 25% out. This guy, again, supposed to be 473, and it's 465. I mean, you can't get much better than that. That's perfect. Okay. So that's the one we're going to replace now. So turn this back over to the area we're working here, and we've got this on there. We're going to take that off, and that goes to that tube socket back there behind the line cord. Okay, getting this in there is a little bit more trickier, but not as bad as the one that was in there. So we just kind of gently move stuff out of our way. I want to come in this way, okay? And so I put it here, put the numbers up, and I see where I got to go. I got to go to that wire, and I need to go to this wire here. So I want to leave about an inch on both sides to center it. So I'm going to leave about an inch, and on this one I am going to put some shrink wrap because there's so much stuff around there. I'm going to break this video up into a few videos, so it won't be so long. Okay, so I'm going to cut this. Since we want about an inch, I'm going to cut this about 3/4 of an inch. Somewhere around there. Put that on. You got to do that the right way. Put that on there. And then wrap it around. Get close to that, but not too close. That's why I cut it 3/4, so I got about a 1/4 inch gap there. And then wrap it around. And if you wrap it straight like that, you get a much nicer wrap. And then all you got is that one loop that's out. Again, don't have to be perfect. It just, you can pull it a little bit and give yourself a little bit play. If your shrink wrap's too close, you can unwrap that side a little bit and then pull it. Kind of get a little gap in there, but it don't matter. Just be careful when you're soldering it. And cut off the excess. Throw it away. Now you can go this way or this way. I'm going to go this way on this one, just because it'll be easier to solder. Put it on there. Now we got the wire in the way, so we got to move it over a little bit. Put a drop of flux. And you want to be more on the inside of the coil, because the problem is going to be more the original wire, not the new wire. The new wire probably could solder it without flux, but the original wire underneath, you definitely want flux to hit it. A little solder on your soldering gun. Probably need to clean this one more time. And touch it on there, and try to get the solder in the hole more so than on the coil. It'll go on the coil, what you want, but you want it to go in the coil. And now it's in there, it's nice, that's pretty good. And since it's a ground one, it doesn't matter too much. Leave a little space. You can't probably tell by what you're looking at here because of the 3D, but I'm about 3/4 of an inch up from that socket. That's why I left a little bit more wire there than I normally would. Now here I got another wire in my way. Since this is the ground side and there's nothing here, these things are way up in the air. They're nowhere near what I'm soldering. And I can even pull it up more. I don't need to worry about coiling it. That way I can just wrap it around the best I can a couple times. It doesn't have to be perfect. Make sure the coil stays on the wire, but other than that, it doesn't have to be perfect. We're only grounding the wire. And once you get it on there like that, since this is going to ground, the capacitor can face down like that. Not a problem. You can still move stuff and see it. Bend it down. That'll tighten the connection. And that's an easy one. Drop a flux. Now I could have just soldered it directly to the chassis there, but that takes a lot of heat, and you put a lot of heat on the component. No sense doing that. Just being consistent with what we've been doing with coiling and putting it on is a much less stressful system because it's not overheating the capacitor or any other components. And that connection is just as good. You might want to put a little bit extra solder than what you would normally do because it is a ground connection. And then cut off the excess. Throw it away. And there we got a good ground. Now the actual lead of the capacitor, cut it off too. Don't cut the solder joint, just cut up to the solder joint. And take that off. Also, if you got extra flux there that you want to clean off, you can clean it off at that point with some alcohol. You know, even the manufacturer didn't do that. You see the flux here. They left the flux, and a lot of them do. They just don't bother cleaning them. I like to clean a little bit, kind of make it look nice. Now, if you see something that doesn't look good to you, let's say that looked like it wasn't a really good solder joint. Put another drop on it like that. Take your soldering gun, get it hot. Hold the trigger in, get it hot. Get a good soldering gun, by the way. This is, a newer Weller. It's not the best, but it's a 140 watts. So 140 watts is fine. Get it hot. Just touch it. Melt the solder, and then come back. Now you got a good solder joint. When you reheat it, it's called reheating the solder. When you reheat it, it reflows the solder. And since I put new flux on, it flowed it nicely. And if I look at it from the side, I can see I have a really good solder joint. It's smooth, it's shiny. The end of the old wire is showing there, but that don't matter because I'm soldered behind that. Everything's good. You know, these were nice and shiny when they were new too. If you see, a solder hump should be like the curve they're trying to do with the coronavirus. It should just be a curve. If a solder hump looks like this, it's just a lump like that, you don't have a good solder joint. You need to reflow it. You need to put some stuff on it and flow it again. See, these are good solder joints. Even that one has kind of a hump, but it's hard to solder on a metal chassis. But it's not bad. It's still pretty big around, and it's still somewhat gradual. This one looks really good, But on these, see, this one's got a little bit of a hump, but, that's not too bad. It's flowed pretty good. But if you see one that's pitted or is just a small hump and not spread out, one that looks like this one, this one goes to ground, so it really don't matter. But let me see if I can move that out a little bit. See, it looks like there's a hole in there where the leads go in. But I can see it's actually flowed pretty good. But look for stuff like that. Because you could have a solder joint that looks like this, or, a hook that looks like this. And they look like, a lot of solder here, little bit here, and none in this crevice, then you don't have a good connection in here. The solder needs to flow between them. You can't see that, but if you got good flow, you know it did so flow between them. So there's some good tips on soldering. Well, now that I got this guy in there, now I can put this one back on because I don't need to get anywhere else under there. If I need to check these components and replace them, these resistors, whatever, I can do that later. But we're good to go. It's not a problem. So now I can go back to this one. We know this one's bad, throw it in the can. And throw this one in the can because I'm done with it. It was just a placeholder so I didn't lose this one. Now this is going to go right there to here. So right where these resistors are, I can bend that one out of the way. It's going to go right there. And I got plenty of room to get it in there. And it crosses this resistor, and it crosses this resistor. Now it actually connects to this one, so it doesn't matter. And it connects to that one, it doesn't matter. But let's say it did matter. Let's say this went somewhere else, and that went somewhere else, like here instead of here. Well, since they're not connecting to the same point, you need to use shrink wrap on both sides to make sure that these leads don't touch. But in this case, they actually soldered to the same place. They do touch. They're supposed to touch. So we don't have to worry about that. But be aware of that. Now, since I've got a piece of this guy sitting around, I might as well use them. There's no sense in wasting it. So, actually, no. You know what? I'm not even going to use it. I'm going to put it only on this side. And the reason being is the only thing it could touch is this. It's not going to touch this. But that's the only thing near it. This side, there's nothing there but wires, and they're out of the way. So there's no need there. So here's the only issue. So what I'm going to do is I'm going to leave this long lead here and go straight to there. Since this is closer to ground, goes through this capacitor to ground, I'm going to let the longer lead stay on that side and the shorter lead stay on the more positive side. And this is the last one I'm going to do on the camera. The others you can see are simple. I'm just going to do them off camera. But I wanted to do a demonstration so you could see, some tricks to soldering these capacitors in. Of course, why they need to be replaced, but also how to solder them in without a lot of problems. And hopefully that's been beneficial to you. So if you found it beneficial, please consider liking the video and subscribing to the channel if you feel led to do so. This supports me, and I appreciate it, and it helps me keep these videos online. But we'll finish this one up. Since this is going to be harder to clip after the fact, I'm just going to go ahead and clip it now. Nope, fell on the floor, I'll get it later. And you notice there's a couple leads here that were there from before. I don't like leaving leads. Again, the spike thing that I was talking about, they can pick up interference and they act like a little mini antenna. Cut those jokers off, even though they didn't cut this one off in the factory because it's on the amplifier. I still, cut them off. Get in the habit of doing that. It's good service work. And some service work is not what you're doing, just what you need to do, but get in the habit of doing things that are beyond the call of duty, and you will go much further. You will have people who do work on you after you're done working on it. If somebody else works on it, they're going to look at it, they're going to notice things. And even if they don't notice things, you know you did a good job. And that right there gives you confidence in what you're doing. This one's being a little stubborn, but I'll get it in there. Just the way the wire is bent. There we go. And see, so that's the way you would normally do a connection with shrink wrap if you're in a spot where it needs it. Okay. Put a little bit more solder there than I wanted to. So nobody's perfect. Sometimes you gotta hold it and then get the soldering gun out of the way. You don't want it to move while it's cooling off. And that one is nasty because I put too much flux on it. You see all that brown? It's flux, but it'll clean right off with some alcohol. And if you're not sure, whether or not it's flowed good because of the brown, just heat the iron and clean the iron off a little bit. Get it a little bit back closer to silver. Okay, so it looks a little better. And then just heat it up again. Then you know it flowed good. Okay, and then this side is going to go here, so we're going to just go straight down to it. Oh, sorry, it goes here. Go straight over to it, and we got the shrink wrap in there, but before we soldered, I want to turn that number. Picking up junk because everything's sticking to my hand. You notice my fingernails are kind of long. I use them as tools. See how that wrap down there? I wouldn't have been able to do that without fingernails. So sometimes you have to use pliers to do what I just did. And if you can't get your fingers in there and grab a hold of stuff, fingernails make good pliers. Okay, so leave the long ends on there. A little bit of that guy. Right near that resistor, so I want to heat it at an angle so I don't get the resistor hot. There we go. And then cut off those wires, the excess wires, throw them away. If you don't get in anything, throw them away right away. If you drop one in the chassis, get it out before you go any further, because you'll forget it. Okay, and that's good. So now we're done with this side except for heat shrink. I strongly suggest if you work on the radios for any length of time that you invest in a good heat gun, and they're really handy. You can do a lot of cool repairs with a heat gun and some shrink wrap. All right, there. Okay, so that concludes this video. You see what I'm doing. I'm going to do the same process on these 4 and the one on the top. But there we have replaced those capacitors. I still know where my electrolytics go because of the red wires, and they're actually easier to get to now. You see how this one, I can pull it out now. I couldn't even get to it before because of that other capacitor. Oh, look at that. Let me pull that out a little more. There we go. I got a nice big lead to connect to. I got a lead there, and I got the other lead here. And there's my hot wire. There's my other lead. Stick these in here. I'll just put these in here and then run a lead up to them, because I can put them in there and wire tie them. They're the same, but I'll put the neutrals together and try to get them where the numbers show. Can't always do that, but if I turn them this way, I guess I can do that, yeah. So I can put the neutrals together and then using shrink wrap, of course, run them to this ground, and then a hot here, and the other hot goes here. And I'll cut that back and just solder it on that terminal strip. If I have to take one end of this resistor out of my way. I might do that anyway so I can check the value of that power resistor. But, you know, anyway, that's where they're going to go, just like that, so people can read them. And they'll be wire tied in there so they don't move around. So I hope you liked this video. Like I said, if you did, please consider giving me a thumbs up and subscribing, and I appreciate it. And we will continue this video to do an IF tuning once we get the capacitors in. Thanks for watching.